All right, folks, so we let I be defined as the square root of -1. So we're on page 6 of the notes. If I do the square root of -1 on my calculator, what we find is that we get a non-real answer, meaning we get an imaginary number. So I is defined as the square root of a negative. I squared is equal to -1. I cubed is I squared times I, which would be -1 times I, or negative I. I to the fourth is I squared times I squared, and -1 times -1 is a positive 1. And what we find is that these powers of I continue to cycle through those four possibilities. So if I have I to the fifth, that would be I to the fourth times I to the fourth, we've already said, is 1. So 1 times I is I. So it will end up cycling through these four things no matter what power of I we cycle up through. Usually they throw at least one of these on the ACT, some I raised to some large power, but I want to show you that you can also figure this out on your calculator. You'll see that you have the imaginary unit down at the bottom. Your calculator is not going to work with the imaginary units, but it can help you figure out what I to some power is. So if I do second decimal point I, we can raise that to the power of 2, and my calculator will show me that it is equal to a -1. So for what we're going to be doing with imaginary numbers, you really, bless you, just need to know these first two powers of I. That I to the first is the square root of a negative, and that I squared is -1. All of these other ones will be helpful for the ACT, but these are the only two I would expect you to have memorized. So what we are going to start with today is we're going to be simplifying square roots, just like we were for a little bit on Friday, while bringing in that imaginary component. So anytime you see a negative underneath the square root, you're automatically going to bring that out as the imaginary unit I. So square root of a negative comes out as an I. Now looking at 27, what's the biggest perfect square I could take out of that? 9. 9's the biggest perfect square, and that leaves me with 3 as my other factor. So now we have I. The square root of 9 is 3. And then we have square root of 3. And all of these items are joined by multiplication. So to write it in, appropriate mathematical form, we would want to put the coefficient first, so 3 first, then the imaginary unit I, kind of like we'd say 3x or 3i, and then the radical, the square root at the end. So 3i radical 3, and that would be our final answer. So that is how we simplify these imaginary roots. Let's go ahead and take a look at the next one. -216. Anytime you see that square root with a negative underneath, you automatically bring that negative outside the radical as an I, as an imaginary unit. Now 216 off the top of my head, I'm not sure what the perfect square factors are, so I'm just going to try dividing it by 16. Nope, 16 didn't work. Let's try 4. 4 worked. 54 I know is divisible by 9. So if I can divide it by both 4 and 9, what's the biggest perfect square we could divide out? 36. So 216 has perfect square factors of 36 and 6. So to write this in simplified form, the square root of 36 is 6. Then we're going to have the I, the imaginary unit, and then the square root of 6. Okay. So folks, I'd like you to go ahead and take out your blue guided practice packet. And we're going to do some more practice with these, catch and release style. So down at the bottom of page 2 of the guided practice packet, we've got the square root of negative 64. Now 64 is already a perfect square. What's the square root of 64? 8. But what's the square root of negative 64? 8i. So anytime you have a negative under the square root, you're going to have to bring out that sucker as an I. Same with the square root of negative 9. What would that one be? 3i. So anytime you have a negative under the square root, you always bring it out as an I. Go ahead and try number 3 on your own. Written in proper form, the final answer for this one would be 3i radical 5. 3i square root of 5. Raise your hand if you got that one right. Super duper. So practicing simplifying square roots. And don't forget, folks, you can always use your calculator to trial and error this. As I said on Friday, and I'll say it again, that list of perfect square numbers in your notes, this list, you will be provided with this during the test, but it would be fairly easy to generate the perfect squares just by squaring every integer that you can think of. So folks, we're going to go back into the notes, and we're going to see how we can add and subtract complex numbers. What I would first like you to write down below all of these problems is complex form. Just like we talked about how it's proper to say 3x versus like x3, complex form is a specific way that we need to write imaginary numbers and their real parts. So complex form looks like a plus bi, where a represents the real part and bi, where we have that imaginary unit, represents the imaginary part. So complex numbers have both a real and an imaginary component. When we just have the I stuff, typically we just call those imaginary numbers. So all of the answers that we get, whether we are solving for solutions for quadratics or whether we are using the quadratic formula later, we always want to have the real part first in the expression and separate from the imaginary part. So let's go ahead and take a look at example 2, where we're going to be adding and subtracting complex numbers. So I've got one complex number, 5 minus 7i. I've got another complex number, 2 plus 4i. If I want to add these together, we're really just going to combine our like terms. So real part plus real part, 5 plus 2 is 7. And then imaginary part plus imaginary part, we get negative 3i. And that is my answer in complex form. So it wouldn't be okay to have this. This is not complex form because the imaginary part is first and the real part is second. So it's considered not correct if they are written in that other order. So real part first, imaginary part second. Looking at B, we are subtracting these two complex numbers. Now, what we're going to do with that minus sign is distribute it into this parenthesis. So it's kind of like having negative 1 times 3. So negative 1 times 3 is negative 3. And then a negative times negative 6i would be a positive 6i. So now I have this complex number and the opposite version of that complex number. From here, we combine our like terms. Real stuff together first. 4 and a negative 3 is 1. Imaginary stuff second. Negative 8i plus 6i is negative 2i. Is that in complex form? Yup. Real part first, imaginary part second. So easy enough, we're just combining like terms. It starts to get a little bit nastier when we multiply complex numbers. I want you to take notice of the difference between this problem and this problem. Here, there is no operation explicitly stated between the parentheses, but anytime I have parentheses next to each other, it is implied multiplication. It makes me so sad on the test when students will take a look at something like this and they'll FOIL it instead of just adding the like terms together. So make sure you're reading those problems carefully to know what operation you are trying to do. In order for us to multiply these together, we're going to FOIL. So the same thing that we use to check our factoring work. The F part of FOIL stands for front times front or first times first. So 4 times 5 is 20. Then outside terms, 4 times negative 2i is negative 8i. Be careful with your signs. The I stands for inside, so my innermost terms would be the 6i and the 5, which gives us 30i. Now the question of the day, when I multiply my last terms, what's negative 2i times 6i? Negative 12i squared. So just like we get a quadratic when we're FOILing our factors, it's kind of like we get a quadratic here as well. We have I squared instead of x squared, an x term, and then a constant. A lot of times students will forget about this squared with the 12, so I'm just putting it on your radar. Be careful of the L part of FOILing. No last name, just Zane. He's that famous. Who is that? All right, folks, so from here, can we combine our like terms? I don't know. Is this common knowledge?
It's pretty common knowledge.
So we've got 20. And that's just 20. And then we've got negative 8i and positive 30i. So 22i. Yeah? Yeah. Now, what about negative 12i squared? This is why up at the top of this page we said, hey, you got to know that if you multiply two imaginary units together, you actually get a regular old integer. So anytime you see an I squared, you always want to simplify it to be a negative 1. So notice that in complex form, I only have real stuff, and the imaginary unit, I don't have I squared there. So what we are going to do is replace that I squared with what it is equal to. Folks, what's I squared equal to? Negative 1. Now, is it negative 12 minus 1 or negative 12 times negative 1? Times negative 1. There's implied multiplication going on, yeah? So there is implied multiplication going on here as well. So usually I draw it in parentheses. That way I know to carry out the multiplication. So then 20 plus 22i. What's negative 12 times negative 1? A positive 12. And now we can put it in complex form with that real stuff together, giving me 32. And the imaginary stuff together, giving me 22i. So always make sure you've got your real stuff first, your imaginary stuff second. And that's our final answer in complex form. What questions do we have so far? It's abstract with this whole, what is I? We're going to get into how I arises a little bit later, but right now we're just kind of getting some rough practice with using the imaginary unit and simplifying expressions involving I. I want you to go ahead and try B. What operation is going on between those two complex numbers? Multiplication. So foiling, go ahead and foil that. Careful with your signs. First terms first. 4. Outside terms, 2 times 3i, 6i. Inside terms, negative 3i times 2 is negative 6i. Last terms, negative 3i times 3i is negative what? I squared. Negative 9i squared. So it's usually that last term that throws students off. We got to make sure that we've got negative 3 times positive 3, which gives us negative 9, and also I times I, which gives us I squared. So we go to combine our like terms, and positive 6i and negative 6i, goodbye. They are gone. So now I'm left with 4 minus 9 times I squared is negative 1. Am I going to subtract or multiply first? Oh, PEMDAS, we're going to multiply first. So negative 9 times negative 1 will give me a positive 9. And, oh, we get 13. So this is why imaginary numbers weren't really just invented. They do have important applications because if I multiply 2 imaginary numbers together, we end up getting something real. So 4 plus 9 gives me 13. When I FOIL these 2 complex numbers, we got something real. I want you to write by these. These are conjugates. We're going to talk about conjugates later. Conjugates have the same stuff, different sign in between. Kind of is like difference of squares in that our outside and inside products cancel so that we get 0 for that b value. So if you want to think of it that way, that is what conjugates are. All right, folks, go ahead and set those notes aside, and we're going to jump back into the guided practice. And we are on page 2. So we have an imaginary number times an imaginary number. Negative 5 times 3i is negative 15i squared. I times I is I squared. We're not going to leave it like this, though, because it's not in complex form. I squared becomes negative 1, so negative 15 times negative 1 is a positive 15. Now, here's what's really wild. If you're like, why have we never heard about these imaginary numbers before? Actually, every number is a complex number. This plain old regular 15 actually has an imaginary component of 0. So any number that you have encountered in the past could actually be written as plus 0i at the end. Aren't you glad you didn't have to do that in grade school? Throw on a plus 0i at the end. So you haven't been lied to up to this point. It's just you haven't had a need for these imaginary units. So we don't have to write that plus 0i. 15 is good enough. On your own, I want you to try number 5 and number 6. My biggest advice on these is don't try to do too many steps at once. I always explicitly show turning that I squared into a negative 1 so that I don't get goofy with the signs. Are we going to FOIL number 6? Yeah, it looks like one. I've got parentheses with binomials in them. But on this problem, our operation is adding. So real stuff plus real stuff. 5 plus 2 is 7. Imaginary stuff plus imaginary stuff. And we get a negative 3i. Flip the page. I'm going to turn you loose on the next The next three. Try them independently and then you can check yourself up here. Always ask yourself, what operation are we doing first? Sometimes students look at this answer and they go, wait, should I try to factor out a GCF of 2? Should we do that? Nope, we're just simplifying it. We're not trying to factor it. We're not trying to do anything crazy by changing the value or dividing it by 2. Once you carry out the operation, you are done. Do make sure that you have the 10 first and the -2 second. Now on this next one, our operation is subtraction. So we're going to distribute that minus sign to both terms in that second parenthesis. So a -3 is a +3. A -5i is a +5i. And now we combine our like terms. 3 and 3 gives me a sum of 6. 2i and 5i gives me 7i. Real part first, imaginary part second. What operation are we going to need to do on number 9? Boiling. 4 times 5, 20. 4 times -2i, so outside numbers together, -8i. 6i times 5, 30i. 6i times -2i is -12i squared. See if you can combine your like terms for this one, putting it in that complex form. Remembering that anytime you have an I squared, there's always implied multiplication going on there. (32 minus 22i). Questions on the foiling or the simplifying? That's gross looking. It's a minus 22i at the end. On your own, try the next three. check yourself on the first two. 26 minus 13i for number 10. Number 11 is a positive 12. Now on number 12, what I want you to notice is we have 2 plus 4i times 2 minus 4i. Same stuff, different signs, sort of like difference of squares, where our outside and inside product should cancel. And what we find is, they do because we get negative 8i and positive 8i. And for that last term, negative 16i squared. So goodbye to the negative 8i and positive 8i. We still have to simplify that I squared to be a negative 1. Multiplying first, we get 4 plus 16, which gives me 20. And that's our final answer. Folks, do we have any questions so far? All right,